Welcome back to Differential Equations. In this lecture, we're going to learn how to solve a very important type of differential equation called a linear equation. They pop up throughout mathematics and, more importantly, in the sciences and engineering. The lecture after this will be taking a look at applications of linear equations. So make sure to thoroughly understand this lecture to get to all the interesting applications in what follows. Okay, now earlier we introduced a property of a differential equation called linearity. So they could either be linear or nonlinear. We are introducing that concept now, but just at a very basic level. Once we progress further in the course, we'll come back to linearity to see its true importance. But for right now, what we'll call a linear first order ODE is a differential equation in this form. We have a derivative of y with respect to x, and multiplying it is a function of x, which we're writing a sub 1 of x. In that differential equation, we also have the y term being multiplied by another function of x, a sub 0 of x. And then on the right-hand side, some function of x, g of x. So we're going to refer to by name a1 and a0, or a sub 1 and a sub 0, as the coefficient functions. It kind of looks like a linear equation back in algebra where you were asked to solve for x, but recall our goal now is to solve for the function y. So there's a similarity, but again, we'll see the true importance of linearity once we progress to second order equations. All right. So first thing we want to do is maybe write this in a more convenient form. We're going to rewrite this basic form of a linear first order ODE into something a little easier to work with. So first thing we can do is divide the whole equation, left and right side, by that function a sub 1 of x. All right, this probably looks complicated, but multiplying y on that left side, you have a sub 0 of x divided by a sub 1 of x. You have a function of x divided by a function of x, which is a function of x. Let's just rename that quantity multiplying y. Let's call that p of x. We're just introducing another name. This is just standard notation for linear first order ODEs. Same thing with that right-hand side, g of x divided by a sub 1 of x is just some function of x, which we'll call, uncreatively, f of x. Now what we have done is converted into what we'll call standard form of a linear first order ODE, which is what we'll be using throughout the rest of this lecture. So we're going to write a linear first order ODE in this form with the derivative of y with respect to x plus some function of x, p times y, equals another function of x. All right. So thinking back to our previous two lecture topics, let's ask the question, is this exact? Now, to do that, we would first have to rewrite our differential equation, the version there, what we're calling standard form. We have to rewrite that in differential form, m dx plus n dy equals 0. So let's go ahead and do that. It works here. Just be careful with getting started. You would probably want to multiply everything by dx. Notice you have two dx terms. You have the version or part on the left side. You have a dx on the right side. You'd want to put them all on the same side. So you can think of maybe factoring the dx out once you subtracted those to the same side. All right, so we get to here. This is now in differential form. We don't know what p of x or f of x is, but we'll just pretend that we do to see where this goes. And we can identify our m and n. Now the question, is this ODE exact? Well, let's check our criteria for exactness using the m and n there. All right, and if you calculate your partial derivatives, you'll find that they are not exact, they're not equal. Now, fortunately, we know what to do in this case. We would use an integrating factor if the differential equation is not exact. Now, this whole topic of linear equations does use an integrating factor, but it's used very differently from how we used it previously in the last lecture on non-exact ODEs. Now, there is some consistency. I'll put up on the screen here, using your work on the screen here, you can actually use your previous version for the integrating factor mu, the function of x version, and you actually get the formula now for mu. It's the integral of p of x inside the exponential function. Now, while we have the formula here, this doesn't tell you how to use an integrating factor for standard form of a linear first order ODE. So we're going to come back to this and take a slightly different use of the integrating factor from how we used it in the last lecture. We will get the same formula down there, mu equals e raised to the integral of p of x, but we'll arrive at it slightly differently. Kind of an alternate use for a linear equation. All right, so that is our goal, which we'll get to. Replacing that formula, which we'll rederive much more appropriately for standard form. Our goal is to find an integrating factor for standard form of a linear first order ODE without having to rewrite it in differential form. So how do we do that? Just from this form? Let's go ahead and get to that. All right, so we're still going to use the same notation. So we'll use mu again to denote our integrating factor. And here we're just going to assume it's a function of x. All right. The first step is very similar to what we did previously with a non-exact ODE. Start off, multiply the whole equation by mu. All right. This is going to be what you do in your work in solving linear equations. And we're going to continue with this through the derivation, the proof of where mu comes from. So start off, multiply standard form, the original ODE, by mu. Worth pointing out, it's written there in red. It must be important. Don't forget to multiply the right-hand side by mu as well. Some students overlook multiplying the right-hand side by mu, and it completely changes your answer. All right. How we continue with deriving the formula for mu, which will also be how we solve these, is we're going to look at this left side as being familiar to something that you might have kind of encountered much earlier in calculus. Now, I don't want to tell you, but I'll give some hints. Take a look at that left-hand side. You have derivatives, there's multiplying, and you have terms with y and its derivative, dy over dx, being added together. So think back through the previous calculus courses you've taken. Where might have you encountered something involving adding, multiplying, and derivatives? Pause to maybe think about it. We'll check in a few seconds. All right, so where might have you encountered adding, multiplying, and derivatives all together? maybe with the product rule. And it's probably not hard to see that that left side looks like it might have been the product rule applied to mu times y. Now, we're just making identification here. They seem to be similar looking if you were to implement using the product rule for mu times y. Let's see where we can go with that. All right, so our goal, what we're going to do is try to find a mu so that if we were to apply the product rule to differentiate mu times y, this is the right-hand side on that goal, we would want it to come out to be the left side of our differential equation. Mu times dy over dx plus mu times p of x times y. What we're going to work through here is how we use this goal to solve for our formula for mu. All right, let's go ahead and calculate, by using the product rule, the derivative on that right-hand side. Remember, mu is only right now a function of x, and so is y. All right, now before we do that work, let's just point out where that goal gets us. If that left side becomes the derivative of mu y, the differential equation above reduces to this, and we just need to now integrate both sides. Now this is where we get if we have the right formula for mu. Let's continue with finding the formula for mu, so that way we can solve this by integrating both sides. We'll come back to this in a moment. All right, so we're going to apply the product rule to that right-hand side. First, differentiate mu, multiply by y, and then add to that mu times the derivative of y. All right, keep in mind here, we're going to try to solve for mu. Notice we have some terms that are similar on the left and right-hand side. Mu times dy over dx, well, we can subtract that from both sides. It cancels out. And we're left with this kind of resulting equation. We can even go further. We can divide both sides by y, and we get this very simple, separable equation for mu. See if you can pause from here to finish deriving the formula for mu. It should look similar to our previous formula for an integrating factor. Pause and maybe give yourself a minute. We'll check in. All right, welcome back. Hopefully this went well. At the very beginning of this lecture, we did put on the screen briefly the formula in terms of m and n and their partial derivatives, how it reduces to mu equals the integral of p of x inside an exponential function. We're going to get the same thing here. So first, let's try to separate. All right, you want to multiply your dx to the left side, divide by mu, and if you integrate 1 over mu du, that'll give you natural log of mu. To get an explicit formula for mu, exponentiate, and you'll get mu equals the integral of p of x inside the exponential function, or mu equals e to the integral of p of x. All right, now that is consistent with our differential form version in terms of m, n, and their partial derivatives, but this is going to be a little more useful for solving linear equations, which we're going to summarize momentarily. So we arrived at our integrating factor formula for a linear equation in standard form. Notice we can easily identify what p of x is This is going back at the top of the screen, standard form. P of x is what's multiplying y, and we just integrate that, put it up in the exponential. That is then your integrating factor. All right, let's go ahead and summarize how all this fits together. Very easy to lose some of you in all this with the work. All right, so let's summarize how to solve linear equations. We'll always be using standard form of a linear first order ODE. All right, and once we have it written this way, we identify P of x as what's multiplying y, and we get our integrating factor, mu, as e raised to the integral of P of x. All right, that's an important formula that'll play a role in the following lecture after this on applications. All right, and let's point out some steps involved in how we would then solve a linear equation. So step one, we're going to find an integrating factor. Now it's worth pointing out this formula for mu, e raised to the integral of P of x, that only works if the coefficient of the derivative term, dy over dx, is 1. So notice up there in the upper left corner, standard form, what's multiplying your derivative term? 1. If there's anything else multiplying your derivative, divide by it, the whole equation, to correctly put your equation in standard form. All right, so step one, find an integrating factor. Step two, multiply the original ODE, both sides by mu. Very similar to exact equations and how we more specifically use integrating factors for non-exact equations, multiply by mu. But the work is now a little bit different. The main difference is once you have the correct integrating factor, that whole left-hand side collapses or simplifies to the derivative of the product mu y, always. That's really important. Once you have your correct mu integrating factor identified, the left side just reduces to the derivative with respect to x of mu y. Don't forget about multiplying your right-hand side by mu as well. All right, and the main theme for our course, we're going to use it here. How do you undo derivatives? Integrate. So we're going to integrate both sides with respect to x. The derivative on the left side cancels out. Integrating and differentiating are inverses. So the left side just becomes mu y, and the right-hand side, it's the integral of whatever mu times f of x is. All right. This is worth copying into your notes, so if needed, pause. And when you're ready, let's advance to some examples. Okay, ideally at this point, through exact and non-exact equations, you get a sense for how to use integrating factors. Since we're now kind of well into the course, I'd actually like you to make an attempt to solve this one on your own. This one is very straightforward. There's really no tricks, just a good example to practice. So pause and maybe give yourself 4 to 5 minutes for this. We'll check in after that. All right, welcome back. Let's go through this one together. So first, ask yourself, is the ODE expressed in standard form? And it is. You have your derivative term, dy over dx, with nothing multiplying it other than 1. you have the y term on the same side, we can identify p of x as the quantity multiplying y. So here we identify p of x as 2, and the integrating factor is very simple. The integral of 2 would become 2x. Again, you can avoid including the plus c there. So you get as your integrating factor mu e to the 2x. I hope that was pretty straightforward. All right, we're going to take that integrating factor, e to the 2x, multiply the whole equation, left side and right side, by mu, which is e to the 2x. Provided you found the correct integrating factor, the left side, this is the important part, always reduces and collapses to the derivative of mu times y. And recall, our mu here is e to the 2x. So what we get, and worthwhile checking going backwards with the product rule, that will give you exactly the left-hand side right above it. All we need to do now is integrate both sides. All right, now this is a good point to just recall your integration methods. A lot of times when you're multiplying functions inside an integral, you end up using integration by parts. And that's exactly what's required here for the right-hand side. I'll put the work on the screen here in case you're maybe a little rusty with integration by parts. Ideally, though, you are not. If you feel like your integration by parts skills aren't where they should be, that's a great thing to follow up with me during virtual office hours. All right, so we have our antiderivative through integrating by parts, 2x times e to the 2x minus e to the 2x plus c. And that's the integral on the right-hand side right above, so let's plug that in. This is all the work. Pause if needed. And one of the nice things about linear equations when we solve them, it's actually very easy to get an explicit solution. Because we have mu times y, e to the 2x times y on that left side, just divide by the integrating factor. Divide by e to the 2x. You'll get y by itself. So we get a nice looking explicit solution, which I actually would like you to do for your solutions for linear equations. It'll be very useful for applications that we're getting to. And we get to here. Notice the exponential terms divide off, 2 of them, but the last term, c divided by e to the 2x, it's going to be a little better for us to identify dividing by an exponential alternatively as e raised to the negative 2x. Recall division, you can rewrite with negative exponents. E to the negative 2x, that's going to be more easily recognizable as a decreasing exponential function. All right, so for the most part, we're done. This differential equation does give us an initial condition, which we can use to solve for c. So you should find pretty easily the value for your integration constant c comes out to 4, and we plug that back in to get this nice looking explicit solution. All right, I don't think there were any tricks or surprises here. When you're ready, let's take a look at a follow-up example. How could this get any worse? This thing seems really straightforward, right? Let's see. So let's take a look at example 2, pause and make an attempt. We'll check in a bit. Have fun. Welcome back. I hope you didn't fall into my trap, and there is one here. Let's just see where we can start off. So first thing, this equation is not in standard form. What's multiplying your derivative here? Not 1, but x. You might have incorrectly identified p of x as 3. Now, 3 is the quantity multiplying y, but this differential equation is not written in standard form. So to put it in standard form, we would divide the whole equation by x. X is what's multiplying your derivative term. Recall standard form, you only want 1 multiplying your derivative term. And that changes p of x from not being 3, that's the incorrect kind of version for what students might identify p of x as, but correctly, p of x would be 3 divided by x. With that, we can now find the integrating factor. We're basically going to integrate that 3 over x. And that goes up in the exponent of the exponential function. All right, so we get to here. The integral of 3 over x just becomes 3 times natural log of x. This integrating factor, though, does simplify. Now, as written, due to that factor of 3 in the exponent, the exponential and logarithmic functions don't cancel, but we can cancel them if we use properties of logs. Bring that factor of 3 in front of the logarithm up into the exponent. Again, a property of logs. And now the exponential function and logarithmic function cancel out. You should find mu equals x cubed here. All right, so what we can do is go back to standard form. This was after we divided by x. And we're going to multiply the version in standard form, everything left and right side, by x cubed. All right, just be careful. There's a factor of x that cancels out. 3x cubed divided by x simplifies to 3x squared on the left side there. Don't forget that the left side collapses to the derivative of mu y, so the derivative of x cubed y. And to undo the derivative, we integrate both sides. Now this one, again, comes down to an integration by parts, which is maybe another tricky part, but hopefully not. The true tricky part here was correctly identifying p of x as 3 over x. Now, the integral of x cubed e to the x, that would actually require you to integrate by parts 3 times. You should be able to do that, but there's a nice shortcut, which I teach in my Calc 2 course, called the tabular method, and the work is right here. It's very useful for repeated integration by parts. And it's very quick. Integration by parts, the normal way, might take several minutes. Here, using the tabular method, several seconds. If you took Calc 2 with me, this should look familiar. All right, the answer here, it's the product of the signed diagonals. The diagonal terms there, those are your UV terms. All right, and if we put all that in, we get our solution, which we can easily convert to an explicit solution by dividing everything by x cubed. And that pretty much does it for linear equations. They're very straightforward and actually simple, provided you correctly write it in standard form. The following lecture, we'll take a look at multiple applications of linear first-order ODEs to the sciences and engineering.